Perfect. So, hello everyone. My name is Jacek Miloszewski. I work at Form3. I'm a software engineer there. And today I'm going to talk about bank payments. So, how bank-to-bank transfers work, and a bit in general how they work, and then what does my company does, how does it fit into that picture, and a little bit about architecture and system design and the challenges. So first, before I can talk about Form3, I need to talk about how bank transfers work. So it's only for bank transfers, so it's not card transfers, nothing, no PayPal or anything like that. It's just like plain bank-to-bank transfers. So imagine you have an account in one bank and there is an account in another bank, and the account in bank A wants to transfer some money to account in bank B. So the banks never directly talk to each other. So there's an intermediate always. So it's like a service, software service provider. It's a SaaS basically. So it's called a scheme. And there are a couple of schemes. Like in UK, there are 3 different schemes. And scheme is like an intermediate that is in charge of moving data moving the payment data between the banks. So in this case, like Faster, there are a couple of those schemes, and like Faster Payments is the most known payment. So this is the instant payment. So whenever you send a payment and then you see the payment has been received in a couple of seconds, that's Faster Payments. There is another one. There is something like BACS, for example. So that's a batched payments. So you have those payments that go for 3 days, for example. Direct debit is batched, is BACS, or usually salaries are sent by BACS. But in this talk, I will use Faster Payments as an example. So Faster Payments, the banks send information about the payment to Faster Payments. So Faster Payments operates some kind of queuing. It's a message. It's a kind of MQ service. So you send the message, Faster Payments receives the message, and it clears them. It clears the payment. So it checks that the message payment indeed is valid, that there are no technical errors, that banks are within their limits. They cannot like send too much, and then passes that information to bank B. Now, Faster Payments or other schemes, they never do the settlement, so they don't actually move the money. They just move the data, and the money is moved by Bank of England. So Faster Payments does actually it tallies up all the transfers between bank and A and B, and every 3 times a day, I think, it sends information to Bank of England, where each bank has to have their own account, and Bank of England does the settlement, so it moves the money between accounts. So my company is a layer here between, it's Form3, it's a layer that sits between bank and Faster Payments. So it provides an API, so in this case banks do not have to use the message interface anymore with Faster Payments, and it handles all the communication with Faster Payments. And it also provides like certain extra services on top of it. So for example, confirmation of payee. I don't know if you know, now these days whenever you make a transfer, you have to fill out the pay details like name, first name and last name, and it matches the account with the name. So this is something my company does. And sometimes in certain cases, like for example when both accounts are within Bank A, for example, we can completely bypass the Faster Payment. So in this case, because normally Bank A could detect it, right? Or both accounts are within the same bank, within their own bank, so they don't have to send it through Faster Payments. But with us, they don't have to do it, so it's a more streamlined process for them. Oh, sorry. So why would anyone need that, right? Because it's another service, and they still have to pay for Faster Payments, and now they have to pay us also on top of that. And this is another software layer where things can go bad, right? So there are a couple of upsides to this. So first of all, there are different schemes. There are a lot of schemes. In the UK, we have 3. But in Europe, we have, I think, 4 schemes. And there is like a whole forest of schemes in the US. And those schemes they were created in a very, very different times. So for example, BACS, it's 1968, so that's, it's 60 years old. All the way to some of the newer US ones, which were just released 3 years ago. And they have very different interfaces. So some of them are message-based, some of them are file-based. Even those message-based, they use different protocols for the messages. Now, these days, there is a standard for those kind of banking message. It's called ISO 222. But even within that, each bank each scheme has their own interpretation, so it's slightly different enough that you have to write a completely different integration for them. So we can, abstract this all away, and we provide nice uniform API that works with all the schemes. Another thing is these schemes are not really incentivized to be very user-friendly. So the banks have to use them because that's the only way. So there is no way they can bypass them. So they don't really have to care about user experience. Their main priority is to be very secure and very reliable. And once they achieve that, they don't tinker with them anymore. So they don't evolve. So this is an example, for example, what you need to do to be certified with faster payments, or to connect with faster payments. So you have to have your data center infrastructure in at least 2 separate data centers, where you have to have hardware security modules to sign the messages that go to faster payment. And you have to connect to a custom MPLS vocality network. So this doesn't go over regular internet or even regular TCP/IP network. And on top of that, you have to keep it all the firmware and all the hardware you have to keep up to date without ever, having a downtime. So you can't really have scheduled maintenance. So we abstract this all away. That's good for smaller institutions that don't really have resources to integrate. But also we have a very big customers like Lloyd's who didn't want to do any of that integration. Now, what are requirements for a system like that, right? So our main requirement was the security, because our customers could forgive us a lot, but never if we actually got hacked. That would be like a company-ending event. So that's always #1 requirement above everything else. A second one is that we have to strive for 100 uptime. I think we have SLA 99 point something. I don't remember exactly how much, but it's very important that we cannot have maintenance windows. So the payments must flow like spice. We have SLA on latency. So it's like 500 milliseconds per transaction, so the instant payments have to be instant. And we have to be able to scale easily as our customers scale. So right now, I think we're doing hundreds of transactions, and we have to be able to scale to thousands of transactions. Another requirement is that we have to have this kind of common API, be able to provide to our customers common API with different scheme integrations. So the schemes are, as I showed, like faster payments or BACS. And we have common API, but we have those gateways. We call them gateways. So these are the elements that interact with the scheme. So in a way, the API is front-end, and we have a couple of backends that interact with different schemes. So we need to be able to have that architecture. And we have over 100 engineers. So we have, it's way too many for a single team. So we have to be able to support multiple teams, whatever we do. So I think I Okay. And last, we need to be able to do multiple independent deployments, so we cannot have release trains. We have to be responsive to our customers' demands. Because it's a smaller company, right? It's a total of 200 people. It's a scale up. So this is what we ended up with in terms of architecture. So we went with the service-oriented architecture with Kubernetes, and it's specifically not microservice because some of the services are very macro. It's like, I think I have some of the code frequency. Yeah. So it's hundreds of, most of that code are actually tests, but still, it's a lot of, these services are quite big, especially the gateways. Because we decided that the application was too big to be a single deployment. And we needed to divide it in order to have those, to accommodate multiple teams with independent deployments, as well as to increase a bit resiliency, because we can't have one deployment taking down the whole system. And we run it in AWS, but we try to be as independent of the cloud as possible. So we run our own database. I will talk about it later. We all run our own queuing. The AWS stuff is really good, like SQS and SNS, DynamoDB, but it's like once you integrate with that, there's no going back, right? So we really wanted to avoid that. So a few words about Kubernetes for people who don't work with Kubernetes. So Kubernetes is a container orchestration system, basically. So you create your application. So you've got your applications, and you pack them in a Docker containers, and you deploy them to Kubernetes cluster. And the main function of Kubernetes is that it allows you to manage those services really well. So it allows you, for example, to scale. Once you deploy your application to Kubernetes, it's called there like a pod or a workload. You can very easy scale it horizontally. So when you have more traffic, you scale out your application, you create more replicas. Of course, for that, your application has to be stateless. Just the state is being kept in a database or queue. But you can very easily scale out or scale back if you have less traffic. On top of that, the deployment, you can keeps your application alive. So for example, when one of the pod goes down, it will restart it. And you have those objects like services, which basically works as an internal load balancer. So even though you have, it's called a service discovery, what Kubernetes does. Instead of addressing your client, which might be internal or external to the cluster, instead of addressing separately pod, it just has one IP of the service, and service does all the load balancing between pods. And also when you create new pod, it gets automatically registered. So that's a very flexible system. And there are a couple of systems like this, like Kubernetes. There is AWS native, ECS, there's Docker Swarm. But this one is by far the most mature. So this is one we went with, and it's open source. It's very popular. It gets like you get for free a whole bunch of very good community managed projects. For example, well, we use like Cert Manager, which is a project that it's an operator that does all your TLS certificate management. Like in our case, we have hundreds of TLS certificates within the cluster, and this project manages them all. So it manages whole life cycle. So all the way from ordering with your provider, like a DigiCert or Let's Encrypt. It does the DNS challenge. Then it renews it as a, when the time is right, and puts it in the right place. And on top of that, it provides you Kubernetes provides you a really good way of creating your own operators. So generally, Kubernetes consists of two main components. So it's a control plane, Well, the Kubernetes application lives. So this is API server. There are the standard controllers, database, scheduler, stuff like that. And there is the data plane, which is basically everything else. That's where your actual nodes on which your pods are located are. So these are in case of AWS, these are like actual EC2 instances. And we went with the managed Kubernetes service. So AWS has this EKS service where they are in charge of the whole control plane. So this is fully outsourced. We never see any of those elements. And we just manage the nodes and everything that happens on the nodes. And that gave us like a very nice balance between the flexibility and extra platform overhead. Because you can go either like fully hand-rolled Kubernetes where you manage everything, but then you have to take care of all this mess, or there is like, I think, AWS Fargate that manages all the infrastructure for you, but then it wouldn't be enough for our particular network and security requirements. So managed Kubernetes it is. So another important bit of our application is the service communication. So for service communication, we use NATS Jetstream. So it's something very similar to Kafka. So it's a queue with persistent storage. So in this case, where you have a service, it sends a service A, for example. It's a producer. It sends the message to the NATS. And in NATS, the message is stored. So and it gets delivered to the topic subscribers, whatever service B or C. But the difference is that it also persists there. So, for example, if the service B is temporarily offline, it gets to get all the messages when it's back online, right? So this allowed us, having this NATS Jetstream in between, allowed us to nicely decouple the system. So in this case, and that's important because teams don't have to interact that much. It's important if you have a lot of teams in a company. Because in this case, service A does not have to know much about service B and C, or even if they exist. Right? It just does some work and puts it on the queue. Service B and C, if they're interested, they take the message and process that information further. And you can go with that a little bit further, and we did. So you don't even have to rely on developers of service A to actually inform everyone that they did something to the resource, which is like maybe a record in a database. Instead, we have a service that is attached to the database, and it detects every time the resource is changed and puts that information on the NATS Jetstream, and then all the services that want to know about it, they subscribe to the topic and they get the information. That reduces even more things that can go wrong, right? And this also creates this improves the resiliency of the system. Because on this example here, for example, we have a scheme that's like FPS, and the scheme creates the messages, right? It creates the transfers. We have a gateway that accepts all the transfer, but before they get all the way to the customer, they have to go through a couple of services, service A and B or whatnot. And you can imagine that service A goes down for whatever reason, like a bad deployment. And in this case, our whole system does not go down with the service. Instead, we can keep accepting the messages from the scheme. That's very important, because that makes huge difference between partial degradation, where we have some delayed transfers, and when we have to actually reject messages from the scheme. So in this case, we can still keep on accepting messages that are being put on the stream. And once once we fix the deployment can read all the old messages, process them, and deliver it to the customer. So system is a little bit crippled, but it's not completely out. So with this kind of like microservice service architecture, like the architecture and the patterns are well known, but it's still a little bit difficult to execute sometimes, right? Like very often you move to this microservice service-oriented architecture, and you end up with having the same problems as before, but a little bit more. Like on top of you have distributed version of the problems you had before. So how we made it work? So we had only a few very hard requirements for the teams. So we have the same language, same database and messaging system between all the teams. And in particular, language is the most important, right? Because obviously, mandating single language is a bit counterintuitive because it's not going to be the best for every application. And not going to be the best for everyone, right? Some people have some specific preference. But having this single language across the whole company allowed us to very easily be aware what other people are doing, what other teams are doing. It allows to easily read code and figure out. We don't have to rely on documentation, for example. We can just open the code and everyone can read it. And also we can very easily move engineers between teams, which is quite important as well. We didn't have any requirements for the design, apart from those couple of hard requirements, so we never actually mandated microservice or anything like that. Teams are free to choose whatever works for them the best, apart from those three. And we have the full service ownership, so teams own everything from the design stage, all the life cycle of the application. So from the design stage all the way to development, testing, maintenance, alerts, and on-call. And we don't even have, we don't have testing team, or we don't have DevOps team. Every team does everything. Even within the team, we don't have people who would specialize in any of that. Everyone is in charge of basically all the life cycle of the applications. That changes very much experience, right? Some teams do a lot of development, but for example, my team is mostly SRE. Most of my time I spend, making sure alerts are better. We have visibility. We have on a dashboard what we need. And the last thing is internal open source model. So very often in the microservice service architecture, you have a feature that would span a couple of services. So sometimes those services belong to different teams. So this can be sometimes very painful, right? Because you ask another team to do something, they put it on the backlog, but they have their own deadlines. 3 months later, it's still on the backlog. And in our case, whoever needs the feature implements it, even if the service does not belong to them, and the team that owns it, does the PR, asks for any changes, but in the end they approve and they deploy the change. And that is actually one of the reasons it's possible, because we use one programming language. Otherwise, it would be quite difficult. So up to this point, this has been all pretty well known. There was nothing unusual about our architecture. The unusual bit is that was the initial point where we started just with AWS, but we expanded to all the clouds. And what we do now is like a multi-cloud offer. So why would you want a multi-cloud, right? You have to have some kind of, in this business, you have to have some kind of multi-regional redundancies. So customers wanted to survive cloud regional outage. These are rare, but they do happen. I think there was big US East 1 last year that took AWS US East 1 for a day almost. But that can be done with one cloud provider, right? You can have multi-region AWS. And the other reason was that UK regulators wanted banks to stop relying on one provider, and that provider was AWS. At some point, when banks started to using clouds infrastructure, they all moved into AWS. So that obviously didn't sit well with the regulators, so they insisted on using multiple cloud providers, both for banks and for partners like us, because we're like a third party for banks. So that's the multi-cloud offer, and with the multi-cloud, with this you know, with a setup that can survive, that you can have a regional backup. You can do it in a couple of different ways. So you can have an active passive. So this is the simplest way. You can have active passive. So you can have main active system with AWS and passive system that is scaled down, deployed by scale down. And in case of outage, you have a disaster recovery scenario. You scale it up, you transfer the data, and then you connect. That's a minimum, but that's okay. But not only it's disruptive, so the switch is disruptive, it also takes varied amount of time, depends how much data you have to transfer. You can do slightly better, like you can have like a always scaled up system on standby, and you can have some continuous data replication that does not block writes, so like some kind of eventual consistency. Something like having basically a read replica that doesn't block them, you know, the main node. And that's better, but then still, when you want to do the actual DR, disaster recovery, the switch, you have to have a break in your service. So the only one that you don't have to is a full active system when you can, where you have two clouds, and you have both clouds participate in transactions and all the time. And also, it's the only one that you actually have a guarantee it's going to work. Because with others, you can be very well prepared, but until you have to do it in production, you never can be sure it's going to work. So we went with active. And basically what we did is we deployed our service, all the services, to not two, but to three clouds, two major ones, AWS, Azure, GCP. So they all have some managed Kubernetes service. They are very similar, but just different enough that it's dangerous to assume they're similar. And our customers can choose where to connect. And the state is connected via database and queuing systems. So we use CockroachDB and NATS JetStream for the queue, and the nodes are deployed in all three clouds, and the nodes form a single virtual cluster across three nodes. That's how the state is being shared between the nodes. So now the question is, why would you go with three clouds, basically tripling your your cloud bill instead of just doubling it with two clouds? And the reason for that is you have to have a tiebreaker. So for example, like if you only had AWS and Azure, and one of them, if there was like a network partition event where one of them goes down, but only partially, so let's say it cannot connect to internet, but internally everything works, you would have like a split brain situation where neither of them would know if it's the one affected by the outage, because there's no way of telling. So that's why you have to have like three or any odd number to have a tiebreaker. In this case, like for example, if Azure goes down, it cannot connect to neither AWS or GCP, but AWS see that it can connect to GCP, so it's the healthy one, and it can still read and write to Cockroach and to Nuts, while Azure cannot, and so the writes are not permitted, or reads, I think, as well. And you don't get into, otherwise you would get into like a split brain situation when both of them would be writing potentially to the same records, and reconciliation would be difficult at the very least. So this obviously provides you a very good resiliency, so it allows you to survive a full cloud outage. The main downside of this approach is that writes to your database take much longer than if you have a single database, right? Because to make sure it actually works properly, you have to make sure that your write only returns when data is replicated to other clouds. And that, even if they are fairly, in our case, we are fairly collocated around London, it still takes much longer than if the database was in a single cloud. I think in our case is between 10 and 30 milliseconds per write. So that's not so much, but it's big enough number that you have to be careful when you design your application and your system. You cannot have too many writes, and you cannot have like too many jumps between your services, because each jump adds a couple of milliseconds just from the nuts, not mentioning the extra time from each service. So last interesting bit about this is the networking. So if we have this virtual cluster, they have to talk to each other somehow, right? To form a virtual cluster. And in our case, all the processing has to be done on private networks. So we can never have, those clusters could never talk over internet. Nothing can go, no matter how encrypted. We were not allowed to use VPN, nothing like that. It has to be all private. So what we did, we actually utilized the data center equipment we already had to connect to FPS. And we installed in the data centers extra switches. And via those switches, we connected VPCs in each and every, in each cloud, talk to the switches. So all the traffic between clouds, and it's not only for the CockroachDB and NAS. Everything in the VPC can talk to all the other clouds, never going via internet. So the multi-cloud verdict. So it's very good in a way. You don't have dependency on a single cloud provider, right? So that was one of the main reasons we've done it. And we can survive full cloud outage, and we can test it actually in production, right? So we know, because they both participate all the time, you can, even in production, you can disable one of them, and you can, without impacting customers. So that's something you cannot have with active passive system. That's a great advantage. The bad is that you triple the cost, basically, which is quite a lot. And you have that increased latency, which somewhat constrains your architecture. On top of that, you have increased complexity, because you have to manage 3 different clusters, and you have to manage 3 different clouds. They are similar, but not exactly identical. So you have to have more people to manage it. The ugly is you have to have, sometimes network issues are very difficult to diagnose in that setup, because you have like a request traveling through multiple VPCs, through data centers, back into some other VPC. They don't happen very often, but sometimes they do, and it's a bit painful to sort them out. And the last bit is the management on the on-prem data centers. So we had to do it anyway because we had already FPS connectivity set up, but without that, like that's also a quite big price to pay, because you have to be able to manage the data centers, you have to upgrade, you have to be able to perform software, have hardware updates, firmware, all this without really having maintenance windows. So that's a bit stressful. So some numbers, what we do. So we handle about, not only in UK, we are present in UK, in Europe, in US. Overall, we have about 500 million transactions in a month, with a total value of 250 billion, roughly. And we serve now over 30% of UK traffic, which is quite a scary number if anything ever goes down. And that will be all. Thank you very much. Exactly 30 minutes. Should go?
So, I send some money to your bank.
Yeah.
That costs me no money to do that.
Yeah.
Where does the money come from?
From bank. The
So
bank,
the bank just
the bank
pays.
pays to FPS. Yes. FPS itself is not a for-profit or company. Really, it's managed by Association of Banks. So I think it's managed by a private company, Vocalink, it's part of Mastercard, but so they operate it, and they are being paid by a company called PayUK, and PayUK is association of all the banks. So yeah, the bank cover the cost of the transaction.
So that number's quite a lot of money.
This is a lot of money. Yes, this is scary, scary amount of money. Yes. Yes, please.
Do your customers get to choose which data center they, or which cloud provider they connect to? Or
Yes.
do you do it like using BGP peering?
Depends. We do both. So with the cloud, yes, they can, because sometimes customers also are security conscious, so they don't want to connect via internet. So for example, they have presence in AWS, they use AWS Private Connect to connect to us or Azure or whatnot. In case of that, and that they can choose, but they cannot choose which data center the payment is processed in, and also they cannot choose even at this point. I think we have on a roadmap to actually add that option, but for now, they cannot choose which cluster the data is going to be processed, because like they can connect to Azure and it goes to NATS, to queuing, but then queuing replicates across the cluster, so you don't know which pod will pick up the work for the particular payment.
Lucky that they connect via AWS, but then Google is the one processing
Yes.
everything.
Yeah.
Nabil? Do you not think a lot, if not all, this technology will be replaced fairly soon with blockchain, considering it offers
Oh, I think it's very sticky. Like those our customers, banks, they don't really move all that fast. It's surprisingly sticky. I mean, Bax is, it's here with us all this time from 1968.
The point of blockchain really, it's not on the bank, it's on the user. The user takes control of their money in a secure way.
Yes.
And it's transacted without relying on a centralized cloud or coding user. I've never actually heard of internal open source before till today, but it's not proper open source.
Yes, it's internal open source. But yeah, I don't think. Well, maybe it's not up to me if they're gonna. If blockchain is gonna be more popular, I'm sure we're gonna have an offer.
The Bank of England, do they legally have to process every transaction?
Bank of England settles payments between banks. So basically, for whatever amount of some period of time, banks lend each other money through the scheme, right? Because they transact and they make a number of transactions, whatever. So they're at the end of this time period, one bank will owe other bank some amount of money, and that's Bank of England settles that. Bank of England doesn't interact with people's account. Sure, go ahead. Yeah.
Okay, when it comes to teams dedicating themselves to a full life cycle of feature requests in a platform, and you say there's no Q&A testing involved, but there must be like responsible for the whole testing themselves to make sure it's all bulletproof.
Yes.
Is there any like cross-training or knowledge sharing, something checking of other teams as well to see if there's any issues
Yes.
with it to kind of like find more optimal ways of improving the process?
So in terms of testing, we do have like there's full staging environment, right? So we do favor like an integration test. So for example, we have this gateway. So my team has like one of those gateway that depends on the whole platform.
Yeah.
And so we have like a local deployment where we develop our application. Like we have basically spin up a local cluster on our Mac, and we pull all the other applications. So we run the integration test. Then there is another batch of integration tests being run but made by us, by the team, in CI, and then the application is deployed to a staging where it simmers for as much as needed. And in staging we are connected to a staging area of the bank. So staging is being as well used by customers. So it's almost like a real payments are flowing through the staging.
We've got time for last
There you go.
one question. I'm sorry, but pub, right? Like you're going to the pub, Oli?
Yeah.
Nice.
We had a power outage in Spain at some point last summer. So I would assume that it's fantastic 3 cloud infrastructures, but are you thinking of different regions of clouds?
Depends on the regulator. So in Europe, the regulators in UK are not particularly concerned about that. So what they want, 3 clouds, and all of them are collocated around London. There are different requirements in US. So in US we have slightly different offer, because in US regulator care about regional disasters basically. So we have, in that case, we use 2 clouds, one in east and one in west, and we also have 2 data centers in east and west. But in that case, they're too far for CockroachDB to work. So we actually have the active-passive with continuous data replication there. We couldn't pull off the active-active because the latency was a bit too much. But yeah, so that's depends on the regulator to answer the question.
Yeah, that's a good timing to wrap up this one. Please join us in the pub later on so you can ask Jacek as many questions as you want. But right now, let's do a quick, Darren. 5-10 minutes. Like, can we agree that we're here 20 past? 20 past? Let's do it. Grab a beer. What are you laughing?